Hello, chemists. Let's talk some atomic mass units. Remember, we introduced this in an earlier video, that atoms are small, which means their masses are also going to be small. So what we introduce here is the atomic mass unit. It's abbreviated sometimes AMU, or you might see it written as just the letter U. It's a unit of mass for matter on the atomic scale. So 1 AMU is equal to 1 U, because these convey the exact same information, just different symbols. But this is also equal to this many grams, 1.6605 times 10 to the minus 24 grams. Now, this 10 to the minus 24, this indicates that this is a number significantly smaller than 1. So 1 gram, what is 1 gram? Well, a normal size 6-sided die might be something close to 1 gram approximately. You can see if that's 1 gram, then something that's 10 to the minus 24 grams must be incredibly small. This is also defined as 1/12 the mass of a carbon-12 atom. All right, so this is just a definition here. Matter of fact, if you remember our video, or the video that I did on conversion factors, these are just a series of conversion factors. Now I'm going to do something here. I know that 1 atomic mass unit is equal to this many grams. This is just from right here. I'm going to divide both sides by this number, 1.6605 times 10 to the minus 24, so that everything on the right-hand side will cancel. And if I take the reciprocal of this number in my calculator, what I get is this. So this tells me that I've got 6.02214 times 10 to the 23rd atomic mass units in 1 gram. So this is just another way of looking at this particular conversion factor up here. So the atom mass in atomic mass units we can get directly from the periodic table. So here's some elements that I pulled from the periodic table. And this number at the very bottom, remember we've introduced this number up here. This is your atomic number, the number of protons at the nucleus. This number down here gives you the mass of an atom in atomic mass units. Units are not listed, but we can regard those as atomic mass units here. So let's take an example. Let's say, what are the masses in U, atomic mass units, for a lithium atom, a chlorine atom, a lithium chloride unit, and a water molecule? Well, I'm going to go ahead and list these down. Water, you might not know what that is at this point in terms of its chemical symbol, but it's represented as H2O. The subscript 2 tells me I've got 2 hydrogen atoms, and not shown because it's understood to be here is there's a 1, telling me I just have 1 oxygen atom. Right? You could say the same thing over here, that there'd be 1 chloride, 1 lithium ion in this lithium chloride unit. All right, so let's see if we can go ahead and determine the masses. Well, these two are easy, right? I can get those directly from the table if we're just talking atoms. Now for lithium chloride, well, all I have to do is add these 2 atomic mass unit values together. So lithium and then chlorine, if I add those together, I get 42.39 atomic mass units for the lithium chloride unit. And then for H2O, water, well, I'd have to have 2 times the atomic mass for hydrogen, and then add on that for oxygen. So here I've got 2 times the atomic mass units for hydrogen, plus the atomic mass units for oxygen, and that's what I get. Now, if you're wondering why am I calling this a unit, well, this is actually an ionic compound. This, H2O, this is a molecule. And we'll distinguish those two in a later video. I want to point out that the atomic mass on the periodic table is an average mass. That's because of isotopes. We talked about this in the previous video. With isotopes, they're going to have different masses because of the different number of neutrons at the nucleus, right? Chlorine 35 has 2 less neutrons than chlorine 37 at the nucleus. Chlorine 37 is going to be more massive. If you average these 2 masses based on relative abundance, the average is 35.45 atomic mass units. So for an example, let's take another example. What is the mass of a water molecule in grams? Well, in the previous problem, we determined what the atomic mass was in atomic mass units. And I have a conversion factor that links grams and atomic mass units. And this is the way that I'm going to write that conversion factor. This many grams per 1 atomic mass unit. And again, this is from the very first slide. I'm writing it like this because, again, I've talked about this in my video on dimensional analysis or unit conversion. I want the atomic mass units here that are in the numerator to cancel those in the denominator. If I write it the other way around with the atomic mass units in the numerator, well, then it's going to be atomic mass units squared and the units will not cancel. So those two units cancel. I'm only left with units of grams. And that would be the mass of a single water molecule in grams, an incredibly small number. So mass defect. What do I mean by mass defect? Well, consider the mass of a proton, a neutron, and an electron. All of these have masses that can be conveyed in atomic mass units. So they're all here. And the question is, could we predict the mass of a carbon-12 atom using the proton, neutron, and electron masses? Remember, we've defined on the very first slide that 1 atomic mass unit is 1/12 the mass of a carbon-12 atom. That means a carbon-12 atom should be exactly 12 atomic mass units. Let's see how well we do. All right, so here's carbon. That tells me I've got 6 protons at the nucleus, this atomic number 6, and this is the mass number, 12. That also tells me now, because I've got 6 protons at the nucleus, I must have 6 neutrons at the nucleus for carbon-12, because this is the sum, this mass number, this is the sum of protons and neutrons at the nucleus. So we got 6 protons, so 6 times its mass in atomic mass units, 6 neutrons, so 6 times the mass of a neutron in atomic mass units. Now I must also have 6 electrons, because if we're talking an atom, the number of protons and the number of electrons have to be the same, so that this atom is electrostatically neutral. So again, take 6 times the mass of the in atomic mass units for an electron. If I add those together, I get 12.09 and a bunch of other digits, atomic mass units. Now, remember, I expected this number to be exactly 12 based on the definition of atomic mass units. This number's too big, right? Carbon-12 should be exactly 12 atomic mass units, exactly. So what is going on here? Well, this is that idea of what we call mass defect. In other words, if I talk about carbon-12 and I think of its nucleus with 6 protons and 6 neutrons, and then in some volume around this nucleus, I've got 6 electrons that occupy some region, again, in that volume around this nucleus. When the protons and neutrons interact at the nucleus, mass is actually converted to energy and released, right, when those protons and neutrons interact. And the relationship that links those two is E equals mc squared. Matter of fact, if you think of the mass of a carbon-12 atom, this is when all the protons and neutrons, electrons are together forming the atom, minus the mass that we predicted, assuming that the particles were individual and we didn't account for the interaction between the particles. That mass defect, the difference between those two, is a negative 0.09893 atomic mass units. This mass right here, right, that's the mass right here that's actually being converted to energy. E is what is our symbol for energy. C is the speed of light. So this is the equation that actually links what happens to that mass. It's actually converted to this energy. So this amount of mass is converted to energy, and the relationship is through this equation here. The point of going through this problem is to show you that while we do have the masses for a proton and a neutron and an electron, we simply can't add them up to predict the mass of an atom, because the protons, neutrons, electrons, they all interact. As a matter of fact, those interactions between the protons and neutrons in the nucleus convert some of that mass into energy. So I hope you found this video useful. Thanks for watching.